Today I'm going to present my PhD work, which is titled Multiscale Simulation and Assessment of the Seismic Resilience of Communities. First, I'd like to explain what is meant by multiscale simulation and what is meant by the seismic resilience of communities. So earthquakes are one of the most deadliest and costliest natural disasters that the world can face. So as we can see here, these are the two deadliest earthquakes that happened in the 21st century. So for example, in the 2004 Indian Ocean earthquake and tsunami, more than 200,000 people died in more than 5 countries. While in the 2010 Haiti earthquake, which is a more recent example, more than 100,000 people died. In terms of the cost of the earthquakes are very costly. So these are the two costliest earthquakes that happened in the 21st century. So as we can see here, the 2011 Tohoku earthquake and tsunami actually costed more than $300 billion, while the 2008 Chuan earthquake in China costed more than $100 billion. So the question is, can communities be prepared to such events to reduce this amount of losses? So can we reduce the 200,000 deaths or the $300 billion cost? So the concept of community resilience has emerged from this need. So community resilience is defined as the sustained ability of the different systems of the community to withstand, adapt to, and recover from natural disasters. And our focus here is the seismic resilience, which is related to earthquakes. So if we look at the functionality of the community before and after the earthquake over time, we will see some aging or some reduction in the functionality of the community due to the aging of the different systems in the community. Then after this, there is some mitigation strategies that is made by the communities to mitigate the losses from the earthquake. So we get cycles from these aging, mitigation, until an earthquake hits the community, where we see a sudden reduction in the functionality of the community represented by this dashed line. Then communities start recovery. So this is the recovery trajectory of the community until reaching the pre-earthquake functionality and even more than the pre-earthquake functionality. So basically, community resilience is this area under the recovery trajectory, and it can be quantified using the normalized integral of the area under the curve. So to quantify this R, or this resilience factor, we need to we need rigorous modeling of the behavior of the community at different temporal and spatial scales. So temporal scale meaning that we need to study the behavior of the community during the earthquake, where the time is 7 seconds. So usually earthquakes are from 30 to 90 seconds. And also during the recovery stage, which lasts for months and even years. And we need also to model the community at different spatial scales, starting from the member level. So we want to know the seismic behavior of a single column or a single beam in a building. Then to the building level, so we want to know, to look at the seismic behavior of the building as a total, and then on the community level, so we want to look at the behavior of the community as a total. So that's why the overall objective of my dissertation is to investigate the seismic behavior of components with different scales in the community, starting from member level, building level to community level, on the seismic resilience of communities, while considering the mutual interdependencies between them. So if we look back at the functionality curve, we can see that the component behavior is in this part of the curve, while the interdependencies are in this part of the curve. So this leads us to the outline of my dissertation. So as I mentioned, they have member level, building level, and community level studies. So if we start with the member level, the first study on this level was related to initial geometric imperfections in wide flange steel members. So in this study, we used the measurements from a 3D non-contact laser technique on initial geometric imperfections in real wide flange steel members to propose a new spectral approach to model these imperfections in wide flange members. And then we looked at the sensitivity of numerical models of wide flange or deep wide flange steel columns subjected to axial load and the lateral drift to simulate an earthquake to these initial geometric imperfections. Then we used different machine learning, regression, and classification methods to rapidly predict the seismic collapse behavior of deep steel wide flange columns, again, as part of special moment frames subjected to axial and lateral loads representing an earthquake. And the third study on the member level is actually focused on another type of, or another steel profile, which is the HSS columns or hollow structural section columns. On the building level, we looked at the seismic debris field generated from the collapse of reinforced concrete moment resisting frame buildings. Then on the community level, first we developed a scalable model for in-event interdependencies in community resilience. Then we employed the developed model to study the interdependencies between the building portfolio, transportation network, and healthcare system in community resilience. Then we used again the scalable model to integrate another social aspect, which is household decisions in quantifying the seismic resilience of communities subjected to earthquake sequences, meaning that the community is not subjected to one earthquake, but it is subjected to one earthquake with its aftershocks. Finally, we have an outreach and education aspect that I want to present towards the end of this presentation. So this is a summary of the work I have done during my dissertation, and due to time limitations of the defensive presentation, I'm going to present one study on each level. So I'm going to present the HSS study on the member level, the building level study, and the interdependencies study on the community level, and the outreach and education dimension that I mentioned earlier. So now let's start with the first level, which is the member level. So now we are looking at single column in a single building only. So here we studied the seismic collapse behavior of HSS columns. So the first question is, what is HSS? So HSS is a hollow structured section type of metal profile. As we can see here on the right, we have two types, either rectangular square or circular elliptical type of HSS. And they are commonly used in many countries, including the US. But in the US, they are mainly used as braces, not as columns as part of special moment frames. So here comes the second question. What is the potential of using HSS in special moment frames? Or why we can use HSS in special moment frames? Actually, there are three reasons for this. First, HSS has high strength to weight ratio. Also, they have high torsional stiffness, which is a main concern in the alternative wide flange steel columns, that they are susceptible to lateral torsional buckling. The third reason, actually, they have high radius of gyration around the weak axis, RY, due to the distribution of steel around the perimeter, as we can see here. So what is the gap, or what are the gaps in the literature? There are many research projects actually focused on only improvements to wide flange steel columns as part of special moment frames like the SAC project, but there are only limited experimental and computational efforts on HSS columns. And in these studies, only few HSS sections were considered and only few parameters are studied. So that's why the cyclic behavior of HSS under combined axial and lateral drift is not yet fully understood. So that's why the overall objective of this study is to develop a totally new seismic design guideline for HSS columns as part of special moment frames. So we did this computationally. So we studied the behavior of 37 different columns with different 17 HSS profiles. So as we can see here, this is the distribution of H over T and B over T for the studied HSS columns. And as we can see here, they are divided into 3 types based on their highly ductile behavior. So a highly ductile column is a column that can reach 4% drift while sustaining the applied axial load according to AISC provisions. So type 1 columns are highly ductile for any applied axial load ratio, while type 2 columns are highly ductile for specific axial load ratios, while type 3 columns are not highly ductile based on their B/T ratio. And as we can see here, the studied columns are distributed between the 3 types. So we studied the behavior of HSS columns under 2 lateral loading protocols. The first one is the symmetric cyclic loading protocol specified in AISC to simulate a far field type earthquake, while the CR2 earthquake is, CR2 lateral loading protocol represents a more realistic drift history based on the behavior of a first story column as part of special monitoring frames. And this loading protocol was developed by Tong Yu based on a system level study. So we studied the behavior of HSS columns, or quantified the behavior of HSS columns using 2 performance parameters. The first one is the post-drift strength ratio, or BDSR, which is defined as the final squash load that the column can reach after reaching 4% drift, and it can be used to quantify the axial capacity of exterior columns in special moment frames, because they are usually subjected to variable axial load during earthquakes, while the other performance parameter is the constant critical axial load ratio, or CCLR, which is defined as the maximum axial load ratio that the column can sustain and reach 4% drift without axial failure. And it can be used to quantify the axial capacity of interior columns in special moment frames, because they are not usually subjected to variable axial loads. So this is the modeling approach we used to develop the finite element models. First, the bottom end was assumed to be fully fixed. We used the fully integrated shell element in form 16 from LS-DYNA to discretize the walls and corners of the studied HSS columns. And the top end is the displaced end, and it's assumed to be also fully fixed except for the 2 directions of the axial and lateral directions. And we used the material 153 in LS-DYNA, and we calibrated the material model parameters to the results from a coupon test on real HSS profiles. So the first step actually was validating the finite element model against the results from a cyclic test on HSS beams that happened here in University of Michigan. So this is the model for the studied HSS beam. As we can see here, the beams were cantilevered vertically. This is the displaced end, or the cantilever end. And to simulate the fact that there is no 100% fixation in real connections, we used these 2 calibrated vertical springs to simulate the flexibility in the bottom connection of the steel beams. And as we can see here, the developed model is able to capture the cyclic behavior of HSS profiles, or HSS members. So as we can see here, there is a good correlation between the behavior of the finite element model and the test. And it also, the finite element model also can capture the final failure shape of the beam and the fracture that happens in the corners of the beams. So let's look at the simulation results. So as we can see here, this is the effect of H/T on both performance parameters under the studied lateral loading protocols. And as we can see here, there is a clear negative correlation between H/T and both performance parameters, with low amount of scatter, meaning that H/T is a strong parameter that affects the axial capacity of HSS columns. We can see the same effect for B over T, but as we can see here, there is large amount of scatter of the data points, implying that B over T is not as strong parameter as H over T, and we found that the dominant failure mode is controlled mainly by H over T.
So, I had a question. Can I ask you a question, clarification?
Sure.
Yeah, so like, I guess I'm having a little trouble because I'm sort of outside the domain. Understanding some reference point like baseline. Is there like another column that's kind of well understood in the field? That how do these results compare with something that's standard in the community?
So actually the standard column is the wide flange column. And the last slide in this part of the presentation, I'm going to compare the behavior of this HSS column and the wide flange steel column.
Okay, great, thank you.
Sure. So we want to use the simulation results to propose new expressions for the axial capacity of HSS columns, and actually this expression that will be compared with another expression that was proposed for to the wide flange steel column. So as we can see here, as I mentioned at the beginning, CCLR is defined as the axial capacity of interior columns. So this CCLR is the expression representing the axial capacity of interior columns, and we simplified this axial capacity into a design tool that can be used by engineers to get the axial capacity, rapidly get the axial capacity of HSS columns based on H over T and B over T. So an engineer will enter this graph with H over T, B over T, and then hit with the axial capacity or the initial axial capacity of the HSS column, and then we used this expression to propose a new highly ductile limit for H over T, and as we can see here, it's in the same format as the current highly ductile limits in the AISC provisions, so it can be adopted in the future provisions. For exterior HSS columns, we did the same thing, but as I mentioned at the beginning, BDSR is the performance parameter related to the axial capacity of exterior columns, and we found that the studied parameters are not the same, or the effect of the studied parameters is not the same for different failure modes. So we found we have two failure modes, a global failure mode and the local failure mode. A global failure mode means that the column fails globally in a global buckling mode, while local failure mode means that there is a severe local buckling that happens at the plastic hinge regions of the columns, and the column fails in a local mode at the end. For the global mode, H over T, B over T, and L over Ry are the main parameters controlling the response, while B over B yield is eliminated. For local mode, B over T was eliminated, but B over B yield has had an effect, a large effect, a significant effect. So that's why we proposed two different expressions for BDSR based on the failure mode, and we can predict the failure mode based on B over T and H over T of the HSS columns using these graphs based on the initial applied axial load ratio. Again, like what we have done with the CCLR, we did the same thing with the BDSR, proposed new expressions for these parameters, and used these expressions to propose new highly ductile limits for H over T of HSS columns of exterior columns. So now let's compare our proposed provisions or our proposed guidelines with the current AISC guidelines. So as we can see here, this is a comparison between the proposed highly ductile limits of interior columns of HSS and the current AISC provisions. And as we can see, there are three zones. The first zone is the green zone, or the highly ductile zone, meaning that the columns here are highly ductile based on our proposed guideline and the current AISC provisions, while the red zone is the opposite. They are not highly ductile based on both. This zone is the interesting zone, which is the unconservative zone. So the columns here are highly ductile based on the current AISC provisions, but they are not highly ductile based on our simulation results, which implies that AISC provisions are not conservative in this area. So this is what Professor Atul asked about, which is a comparison between the axial behavior of HSS columns and the axial behavior of the wide flange steel columns. So this is the CCLR, or the axial capacity of interior columns, based on the expression I just showed, and the CCLR of wide flange steel columns based on the expression developed by Tongyu. And as we can see here, for columns with weight less than 100 pounds per feet, HSS columns provide higher axial strength than wide flange steel columns. So that's why it's recommended that HSS columns can be used in special moment frames in low to mid-rise buildings. So to summarize the outcomes, or what was done in this study, first, the response of HSS columns under combined axial and lateral loading was investigated using a validated computational model, as I showed. We studied the behavior of HSS columns under two lateral loading protocols, symmetric cyclic and CR2 protocol. We found that HSS columns provide higher axial strengths than wide flange columns for weights less than 100 pounds per feet. And the proposed high ductility limits suggest that current AISC limits are unconservative for H over T. So now let's go bigger. So we finished the member level. Let's go to the building level. So now we are looking at the behavior of a whole building. So in this level, we studied the seismic debris field generated from the collapse of reinforced concrete moment-resisting frame buildings. So what is the motivation behind this? Actually, collapse of buildings is one of the most catastrophic consequences of earthquakes. As we can see here, it produces large amount of debris, which may hinder the emergency and evacuation operations. So this is the collapse of a 17-story reinforced concrete building that happened in 2016 in Taiwan. And as we can see here, the collapse of this building actually totally blocked the adjacent road. So this cascading effect of debris accumulation affects the seismic resilience of the road network and the whole community. Another recent example for this is actually the 2010 Haiti earthquake that produced around 13 million cubic yards of debris, and it took years actually to remove this debris from Haiti because of the poor resources that were available in Haiti at this time. So what is the gap, or what are the gaps in literature? So there are many studies here available to quantify the amount of debris, but in tons, like in weight. But there are fewer studies available to assess the extent of debris around collapsed building, like how far the building will go in each direction around it. So most of the available studies on the extent of debris assume the predefined shape of the debris field, and only one study that is based on a more rational approach, which is the applied element method, or a computational approach, but it was focused only on masonry structures, which go only from 1 to 3 stories. But we found, as we saw from the previous slide, reinforced concrete buildings can go higher and can cause more severe effect on the road network. So that's why the overall objective of this study is to assess and to characterize the seismic debris field generated from the collapse of reinforced concrete moment-resisting frame buildings. So the modeling approach here is a different one from what I have showed before. So this approach is the applied element method. So in the applied element method, the structural elements are actually discretized into small rigid cubes, and these cubes are connected together using a set of normal and 2 orthogonal shear springs distributed along the element faces. So this is an example of a 3D frame modeled in the applied element method. So as we can see here, each 2 elements are connected together using, this is the set of normal springs, and this is the set of 2 orthogonal shear springs. And actually, the displacements are evaluated at the spring locations, not like the finite element method where the displacements are evaluated within the elements. So that's why this approach is faster to simulate the collapse of the building compared to the finite element method. And each group of springs actually represents a constitutive relationship for the material. So the normal springs represent the normal behavior of the concrete, the compression and tension. The shear springs represent the shear behavior of the concrete, while the reinforcement bar are represented by another set of springs that represent the cyclic behavior of the steel reinforcement. So again, like what we have done on the member level, the first step is to validate our model against the results from real experiments. So that's why the applied element modeling approach was validated against the shake table test of a typical multi-story RC frame building that was conducted in China. And the test building actually was scaled from a nearly collapsed real building during the 2010 Yushu earthquake in China. But due to limitations on the shake table test capability, only 2 bays of the original building were designed and tested at a scale 1 to 5. And these are the constructional drawings of the test building, and this is the applied element model of the test building. So as we can see here, this is a comparison between the behavior of the building in the test and the behavior of the building, or the applied element model of the building. And as we can see here, the applied element model is able to capture the collapse behavior of the building, and more importantly, it can capture the final debris shape after the building collapse, which is the focus of the current study. So we developed applied element models of a prototype building that was designed and outlined by Hasselton. So it's a seismically designed moment frame reinforced concrete building. So as we can see here, the prototype building has 4 moment resisting frames in each direction. And we considered 3 different heights, 4-story, 8-story, and 12-story, and this is the applied element model of the 8-story building. And each building each building was subjected to the 22 ground motion records specified in the far field record in FEMA P695, and each ground motion record was actually applied 2 times, one at 0 degree, meaning that the X and Y axes of the ground motion are the same as the X and Y axes of the building, and at 45 degree, meaning that the X and Y axes of the ground motion were rotated by 45 degrees. So based on the simulation results, we found that the buildings are collapsing in one of 4 modes. Mode 1 means that the building is collapsing in X direction, aligned in X direction, while mode 2 means that the building is collapsing aligned but in Y direction. And as we can see here, this is the extent of debris around the building. Dimension A is always the largest dimension, B is the corresponding dimension, C and D are the other dimensions. We can see also these are the second modes, like mode 3 and mode 4 are skewed collapse mode, while mode 3 is skewed towards X, mode 4 is skewed towards Y. Again, A is the largest, C is the second largest, B and D are the corresponding dimensions. So we want a tool that can be used to classify these collapse modes without doing the analysis again. So machine learning actually can help us to do this. So that's why we used deep neural networks to classify the collapse mode based on input parameters. So the input data set here is 132 collapse cases, which is like the 3 building heights times 2 ground motion orientations times 22 ground motion records times 5 input parameters or input features, which are the B ground acceleration ratio X over Y, B ground velocity ratio, B ground displacement ratio, RES intensity ratio, and the number of stories. And we actually used the symmetry of the building around X and Y to augment the data to increase the size of the data set from 132 to 264. And this is the architecture of the developed deep neural network. So we used 2 hidden layers with 10 neurons in each layer. And as we can see here, the output class is one of the 4 classes that I just showed, mode 1, 2, 3, and 4. And actually, the deep neural network was successfully able to predict the collapse mode of the studied prototype buildings with an accuracy of 92% for training data and 82% for the test data. So let's move to the extent of debris. So now we classified the mode of collapse. Now let's move to the extent of debris, which are basically the dimensions that I showed in the earlier in the collapse modes. So dimension A, B, C, and D. So as we can see here, we can notice that the debris is generally thrown in one primary direction based on the gap between the blue line representing the largest dimension, which is dimension A, and the other lines. And we can see also that the larger dimensions become more dominant than the other dimensions as the building becomes taller. And we can see this by the increased gap between the curves as the building becomes taller. We actually tried developing applied element model for another building or another prototype building, which is non-ductile frame building. So non-ductile frames are buildings that were designed according to old codes. And we found that actually the extent of debris for older buildings is quite similar, like the extent of debris of the studied prototype building. However, the big ground acceleration that induces collapse is different between both buildings. So again, we want to develop a tool to be used in the future to rapidly assess the extent of debris. So that's why we fitted our data into a log normal distribution for the debris extent, or to evaluate the extent of debris probabilistically. So now let's see the urban planning implication of such a study, or what is the effect of the collapse of the building on the community. So as we can see here, this is a comparison between the collapse of rear reinforced concrete frame buildings caused in the 1999 Izmit earthquake in Turkey. And this is the debris field from the developed applied element model. So this is not a rigorous validation because like what I have shown before, because the information about the buildings here is not known, but this gives a sense of how this tool can be used on the community level. And here is a schematic diagram for the interaction between a collapsed 4-story prototype building with a 3-lane road. And as we can see here, a 4-story building can actually block like 50% of the adjacent 3-lane road. So we provide a simple linear tool to be used by urban planners to get a sense of the maximum extent of debris they can expect from the collapse of such buildings. So this is the normalized dimensions with respect to the height, or the normalized maximum extent. And this is it's only function of the number of stories. And we fitted three expressions, one for the median, one for the 10th percentile, and one for the 90th percentile. So to summarize what was done here in this study, the extent of debris around collapsed RC moment resisting frame buildings was estimated using a validated computational approach, as I showed, and the dimensions of the debris were characterized using a log normal distribution. We used linear regression to propose estimate for the maximum extent of debris as a function of the building height. Actually using these proposed expression with the deep neural network can enable rapid assessment of roadway blockage in disaster planning exercises.
So Omar, I had a question.
Yeah, sure.
Like you mentioned direction, that there was a primary direction of collapse earlier. So is that predictable in the sense, so you can predict which way the building is going to fall if it collapses? And could that be, is that useful for planning purposes, or is that not so predictable because the load, I mean, I'm thinking that maybe the earthquakes, the load is not as predictable. I'm thinking Jenga or something like that. Like if, you know, it doesn't, we can't predict which way it's going to fall that well, right? So because maybe the load isn't known, the forces aren't that predictable. So how sensitive are these predictions to sort of randomness in earthquakes in some sense? Like,
So that's why actually we used the deep neural network to classify the mode of collapse based on the input parameters. So there are some input parameters that can capture the behavior of the earthquake, like the big ground acceleration, the RES intensity, which represent the area under the ground motion. So it can be predicted based on these input parameters, like the mode of collapse. Like what I've shown, mode 1 to mode 4, will it collapse in an aligned mode or an skewed mode?
I see. Okay. So does that imply that like you would know which way the building is going to fall, whether it's going to fall towards the road or away from the road, for example?
No,
towards
for this like away, like if we know that it will collapse in X direction, for example, to the road or away from the road, that's as you mentioned, that's a random, and we actually used a uniform random number distribution to classify this direction. But in which axis it will collapse, that's the deep neural network.
Okay, so you're saying the axis is more predictable,
exactly,
and could be used for information. So like if you're putting multiple buildings next to each other, does this influence the orientation in some sense, possibly, so that buildings don't fall onto each other or something like that?
Yeah, so usually in the city, the buildings are not in the same orientation. So some buildings will be rotated by a single angle. So not all the buildings will get the same ground motion resolution or the ground motion record. So that's how can we predict the collapse axis of the building. So it will be different between the different buildings in the city. And actually, that's what I'm going to do on the community level as well.
Okay, nice. Okay, thank you.
Okay, so now let's go larger. So we are going from the building level. So from looking at single building to look at a whole community. So here we studied the interdependencies between the building portfolio, which is actually the collapse of the building, as Professor Atul mentioned, transportation network, and healthcare system in community resilience. So actually, to discuss the motivation behind this research, severe earthquakes actually produce catastrophic social and economic losses, like what I have shown at the beginning of the presentation. So communities should be prepared to such events. And actually, there are complex interactions that arise between the different systems in the community. So this is an example of the interactions that can happen between the three studied systems. So for example, between the transportation network and the healthcare system. So the number of trips made between the building location or the injury location and the hospitals actually adds load to the transportation network in the community. At the same time, the functionality of the transportation network, like the travel time, controls the number of trips that can be made between the hospital locations and the building location. So these mutual interdependencies actually profoundly influence the first response activities and can extend to long-term recovery. So dynamic analysis is actually required to model these in-event interdependencies in community resilience. So what are the problems? Again, what are the gaps in the current literature? So there are previous studies focused on the behavior of each system independently, like these studies are focused on the building portfolio. These studies are focused on the healthcare system, and these studies analyzed the transportation network. But there are key limitations in these models or in the available models when considering the mutual interdependencies between these systems. And that's why the objective of this study is to develop a new highly modular, multidisciplinary simulation model to model these mutual interdependencies between the building portfolio, transportation network, and healthcare system in the community. So in this proposed model, the capacity of the transportation network is simulated as a function of the combined effect of the bridge damage with the new aspect here, which is the accumulation of debris resulting from the collapse of the buildings. And then the transportation network model is incorporated into a discrete event simulation to model the response of the healthcare system as well as the debris removal in the community. So this is the proposed simulation model. As we can see here, it's highly modular, where each aspect in the community is represented by a single black box, or what we call simulator, that can be actually replaced by another higher fidelity one. And this model takes input and provides output to other simulators in the model. And as we can see here, each of the three systems is represented by a set of simulators. Like these simulators are related to the transportation network, these simulators are related to the building portfolio, and these simulators are related to the healthcare system. And this highly modular setting actually enables a future expansion of this framework, for example, to add another aspect like the lifeline systems or any other social aspect. And this simulation model actually runs on different stages with different time scales. And this is the temporal scale that I mentioned at the beginning. So we have simulators that run before the earthquake to model the behavior of the community before the earthquake. And we have another simulators that run each time step during the earthquake, which is in terms of seconds. Then another simulators that run after the earthquake to assess the seismic losses. Then the last simulators run during the recovery stage, each time step, where the time step is in days. So as I mentioned at the beginning, this simulation model combines the effect of bridge damage and debris accumulation. So bridge damage, there are many models available to assess the bridge damage. Here we used the hazardous methodology, but the debris generation, that's the new aspect here. So actually the community is consisted of many types of buildings, like masonry, wood, steel, reinforced concrete, and other. So that's why we adopted different methodologies for assessing the extent of debris generated from each of the collapsed buildings. So for the masonry buildings, we used the results from this study, which assumed that the extent of debris of masonry buildings will be larger than the area of the buildings by the factor epsilon. So this was actually based on another applied element model approach for masonry buildings in Italy. And as we can see here, it's function of the building properties. For the reinforced concrete buildings, of course, we will use the results of the study that I just mentioned on the building level. And for other buildings in the community, we adopted this assumption of the 3D triangular prism of the seismic debris. For the traffic simulation, we adopted the four-step model to simulate the behavior of the traffic network or the transportation network, where the first step is the trip generation. So in this step, the trip productions and attractions are evaluated between the different zones in the community. Then the second step is to distribute these trips between the different zones. Like the output of this step is what is called origin destination matrix, saying that this amount of debris will go from zone A to zone B, and this amount of trips will go from zone B to zone C, and so on. Then the third step is the modal split, which splits the OD pairs between the different available modes of transportation in the community. The fourth step, which is the last step, is actually traffic assignment. In this step, we adopted the user equilibrium model, which is basically an optimization problem that minimizes the travel time in the road lengths. So these two steps, like the first and last step, are updated during the recovery stage to reflect the mutual interdependencies that I just mentioned. So the trip generation are actually, or the trips are actually updated in three ways. First, the trips made in the healthcare system are added to the trip generation step. The trips made to remove debris from the community are added to this step. And the trips are actually reduced based on the reduction in the functionality of the buildings in these zones. For the traffic assignment, this step is updated to reflect the reduction in the capacity of the roads due to totally blockage or partial blockage from the debris or the building damage. And these are changing during the recovery stage as the debris is removed and the bridges are repaired. So this is the discrete event simulation of the healthcare system. I'm not going to go into details on this study, but I just wanted to show how the healthcare system is simulated in this model. And all the assumptions here are based on data from real earthquakes, like the response of real hospitals to real previous earthquakes. The same thing with the debris removal, which is simulated using the same technique. So to showcase the capabilities of the proposed simulation model, we tested our model through a case study that is focused on the seismic resilience of a part of Memphis city in Shelby County in Tennessee. And this community actually consists of more than 8,000 buildings, and the transportation network consists of more than 300 nodes, 500 links, and 200 traffic analysis zones. So as we can see here, this is the archetype community with the location of bridges, hospitals, and other aspects. And this community was subjected to the 7.7 earthquake scenario specified by USGS for this area. And as we can see here, we can monitor the dynamic behavior of the buildings in the community, returning from the not functional state to the basic or full functionality state. And we can see this reflected by the physical functionality index of the community after the earthquake. And as we can see here, it takes years for communities to return back to the full functionality from earthquakes. For the recovery of the transportation network, we can look at the same effect. So immediately after the earthquake, we can see here that there are significant number of links that are closed due to debris accumulation or bridge damage. Then after 1 month, significant number of these links regained their functionality. After 12 months, everything is back to normal. And as we can see here, there is high demand around the hospital location immediately after the earthquake. So the question now is, can this community perform better? Or in other words, can we use our simulation model to study different what-if scenarios, like if we did this, what the gain we will get? The question is yes. And that's why we tested 3 different mitigation strategies on this archetype community. The first one is related to the building portfolio, which is basically upgrading the seismic design of buildings, or in other words, making buildings stronger. For healthcare system, we increased the number of ambulances, added a field hospital, enhanced the emergency response of the rescue team. For the debris removal, we increased the number of trucks available to remove debris in the community and increased the number of debris or temporary debris management sites in the community. So we can see the effect of these mitigation strategies on the behavior of the transportation network. So as we can see here, upgrading the seismic design of the building leads to less number of collapsing building. So as we can see here, this is the improvement in the initial functionality of the transportation network just after the earthquake. And we can see this also reflected on the travel time on the transportation network. We can see the same effect, or the effect of the mitigation strategies related to the healthcare system on the number of injuries waiting admission to the hospitals and the mobilized injuries inside the community. So to summarize what was done in this study, first, a multidisciplinary simulation model was developed to model the mutual interdependencies between the building portfolio, transportation network, and healthcare system in the community. Then we showed the capability of the proposed simulation model through a case study. Then we found that upgrading the seismic design of buildings and increasing the number of trucks actually increased the seismic resilience of the transportation network. Actually, choosing the appropriate mitigation strategy is not an easy task. It's a challenging task because it depends on many factors beyond just the economic cost of this strategy. So this simulation model actually can be used by decision makers in the community to make such trade-offs or study what-if scenarios, like what is the trade-off between the economic cost of a specific mitigation strategy and the social gain that we can get from this mitigation strategy. So now let's move to the outreach and education aspect of this work. So we took the results from the building level study and the community level study and integrated it into a virtual reality model that was developed actually by Andy in our research group. So this is me trying the model in a virtual reality set, and we can actually look at the collapse sequence of the building, flies through the city, and look at the collapsed buildings like we are inside the in the event. And as we can see, there's also some sound effect of the earthquake. We can also move through the city and see the effect of the building collapse on the road network. And this can be used to educate people in the community about the effect of earthquakes on their community. So let's conclude with the key contributions of my dissertation. So here I'm going to present the key contributions of all the studies that I conducted, the ones that I showed here, and the ones that I didn't show. So first, a spectral approach that modeled the initial geometric imperfections in wide flange members was proposed based on the measurements from a 3D non-contact laser scanning technique. And then we studied the sensitivity of numerical models of wide flange columns to these initial imperfections. We used also different machine learning classification and regression methods to predict or rapidly predict the seismic collapse behavior of deep steel wide flange columns as part of spatial moment frames. Also the seismic collapse behavior of HSS columns that are part of spatial moment frames was studied, as I showed, under combined axial and lateral drift. And based on the simulation results, new highly ductile limits for and design guidelines for HSS columns as part of spatial moment frames were proposed. On the building level, the seismic debris field generated from reinforced concrete moment frame buildings was estimated using a validated computational approach. The collapse modes were classified using a deep neural network, and the extent of debris was modeled in a probabilistic manner and characterized using linear regression analysis. Also, the effect of the era of the building code was studied on the debris field extent. On the community level, first, a scalable model that employs a simulation-based dynamic analysis was developed. Then this model was employed to model the interdependencies between the building portfolio, transportation network, and healthcare system in the community, like what I showed. The effect in this model, the effect of the damage of bridges, was combined with the new aspect here, which is the accumulation of debris resulting from the collapse of the buildings. Also, the developed scalable model was employed to integrate post-earthquake household decisions in quantifying the seismic resilience of communities subjected to earthquake sequences. To this end, incremental dynamic analysis was used to develop new fragility curves for main shock damaged structures, which were distinguished from the conventional fragility curves of intact structures. Finally, I'd like, of course, to thank my advisors, Professor Sharif Al-Tawil and Professor Jason McCormick, for their continuous support since I came here to University of Michigan. I'd like also to thank my committee members, Professor Seymour Spence and Professor Atul Prakash, for their constructive comments during our regular iCore meetings. I'd like also to thank the members in Professor Tawil's research group, Tong Yu, Suyun, Andy, Yunsu, Andrew, and Sakif, and the members in Professor McCormick's research group, Christian and Malcolm. Of course, I'd like to thank my family and friends for always supporting me. And finally, I'd like to thank the founders of this research, NSF and NEST. So this dissertation, or the work of this dissertation, actually was published in 3 published journal articles, 4 under submitted journal articles and under review, and 1 in preparation journal article, and 1 in preparation magazine article related to the outreach dimension that I just showed. So with this, I'd like to thank you all for your participation, and I'm